Rotating frames. Consider an object whose position is given by vector r that rotates along some axis with angular velocity omega. We can define angular velocity as a vector along the direction of the axis of rotation. What are the consequences that now the angular velocity is a vector? For example, we know that velocities add for different frames. If we have velocity of object 3 relative to frame 2, and we add velocity of frame 2 relative to, for example, frame 1, we're gonna get velocity of object 3 relative to frame 1. Angular velocities work exactly the same way. So what we expect to get the angular velocity of object 3 relative to rotating frame 2 plus angular velocity of, say, frame 2 relative to frame 1 is going to give us angular velocity of object 3 relative to frame 1. So it gives us a lot of flexibility and convenience when we define angular velocity as a vector. Another important advantage is that we can write velocity for any point described by vector r in a very compact form, that velocity will be angular velocity cross vector r. So this is both very useful and compact. For example, if we consider some unit vector fixed to the rotating body, then using the formula above, we're gonna find the rate of change of this vector will be given by angular velocity cross the vector itself. Next, we would like to extend this result to a rate of change of some arbitrary vector defined in rotating frame. Imagine the following scenario. We have S0 defines the inertial frame given by axis x0, y0, and z0. Omega defines angular velocity relative to inertial frame S0. Reference frame S will be the rotating frame. Let's consider some arbitrary vector q. This could be anything, for example, position or velocity, force, etc. Our job is to relate the rate of change of this vector relative to inertial frame and change of the same vector with respect to time relative to rotating frame. We write vector q in orthonormal basis in reference frame S. Orthonormal basis in S is fixed. It rotates with frame S. Therefore, we can write that the rate of change of vector q relative to frame S will simply be given by the sum of time derivatives of individual components with respect to time times the relevant unit vector, E sub I. On the other hand, the rate of change of the same vector q with respect to inertial frame S naught will have the same sum dq I dt times EI plus, using the chain rule, we'll also have to compute the rate of change of each of the vectors that are now rotating relative to the reference frame S naught. We saw previously that the rate of change of a fixed unit vector relative to non-rotating frame is given by the cross product of angular velocity times the vector itself. We use it and rewrite the second term as sum of components qi times cross product of angular velocity and the vector E sub I, which we write as angular velocity omega cross product, and we move the sum inside this cross product, and we get q sub I times E sub I, which of course is nothing other than just vector q. So we can go back and simplify the expression above. We note that the first term, this term here, is just the rate of change of q relative to frame S. Whereas the second term we have shown to be angular velocity omega cross the vector q. In other words, the rate of change of arbitrary vector q relative to non-rotating frame is equal to the rate of change of this vector relative to the rotating frame plus angular velocity cross the vector itself.